All right, here we are again. So today we're going to do chapter 7. So we're completely done with chapter 6. Actually, let me go get Moodle open for a second. And let's see where we are. Okay. All right, so 7 is here. I made sure I put it in there. One thing that is missing, I'm going to put it in there right now, is a couple of charts that we might need to do the calculations in this chapter. The charts are not absolutely necessary, but sometimes it might be a little quicker and easier to use them. So hold on one second. All right, so we're complete now. So this week we'll probably end up getting through chapters 7 and 8. And then of course there'll be 2 more problem sets. And now just because this is such an intense class, we've already decided that the first midterm was due on the 11th, which is a week from today. The second midterm is actually based on chapters 6 and 7. So already maybe by the end of this week, we'll be ready to start at least looking at the second sample midterm. So yeah, there's no time to rest in this class. We've got to be constantly on the go. But today we can just go through chapter 7. It turns out to be one of the more important chapters in the course, and in fact in all of statistics. And so we want to make sure we understand this material very, very well, because we'll see this discussion. Every one of the later chapters will have this in it somewhere. And especially, and if you take another class in statistics or other applied areas that use statistics, what we're doing today will be extremely important. So now I did want to mention one other thing too. There's a few people who have not yet sent me the chapter 3 and 5 problem sets. So that if you're in that category, you should take care of it today, because this is the kind of class where we don't really have a lot of time to waste. So they're not corrected yet, but let's face it, we want to get that done sooner rather than later. All right, now let's get to chapter 7. What is this mysterious chapter 7 all about that's so important? Well, you might remember chapter 6 was all about discrete probability distributions. Now, what is it that makes a distribution discrete? It's the idea that you can only have a finite number of possible values. So if you recall, in fact, let's just quickly review this just for a minute. In chapter 6, we were introduced to the concept of a random variable as well as a probability distribution. Okay, where are we? Here we are. So yes, this is where we first introduced random variables and probability distribution. So we had to define these concepts, and we did mention along the way that random variables and probability distributions can either be discrete or continuous. So discrete simply means that there's only a finite number of possible values that a random variable can assume. So for example, if you flip a coin 10 times, and X represents the number of heads, then clearly X can only have a value of 0, 1, 2, 3, 4, 5, all the way up to 10, which means you have 11 possible values. And that means that X has a finite number of possibilities. And therefore, in that case, you would be looking at a discrete probability distribution. Okay, only a finite number of possible different values. Okay, so we also introduced 2 very important cases of discrete probability distributions. Let's go jump ahead and find them. The binomial and the Poisson. So if you recall, the binomial distribution is used when we have a series of independent trials, and on each trial, there's only 2 possible outcomes. With Poisson, we're looking at cases where time is elapsing, and we're trying to analyze the number of events that can occur during that time interval. Okay, so we introduced a probability formula for both of them. This was our formula for calculating binomial probabilities. And we also had a formula for calculating Poisson probabilities. Let's jump ahead here and find it. Oh yeah, there it is. That's the one that includes E, which is approximately 2.7183. And then of course, lambda represents the average number of events that can occur over a given time frame. And then of course, this is our old friend X factorial. We all know what that is. And also we did note that there are special formulas for calculating moments in these two cases. For the binomial distribution, the expected value is simply n times pi. The variance is n pi 1 minus pi. And then, of course, the standard deviation is always the square root of the variance. And that certainly makes things a little bit simpler for us. For the Poisson distribution, we have a similar situation, except here the formulas are even simpler. I mean, it doesn't get much simpler than this. The expected value is lambda. The variance is also lambda, and that means, of course, that the standard deviation is the square root of lambda. Okay. And then we also looked at histograms that explain or describe the distribution for both of these two distributions. For example, this is what the histogram looks like for the Poisson distribution when lambda equals 1, when it equals 2, and when it equals 5. So of course, because this is a discrete random variable, you have a series of bars, one for each possible value of x, and the height of each bar represents that probability. And the key here is that you only have a finite number of bars, all right? And similarly to the, up here we did the same thing with the binomial distribution. Let's see if we can find that. Let's see, oh, come on, they're here somewhere. There we go. All right, so here, in this case, we have the binomial distribution when there are 10 trials. First, we looked at the case where pi equals 0.2, and it does kind of look like the Poisson a little bit. There's a discrete number of bars. Mostly they are clustered around the low values, 1 and 2 for the most part, and the rest are less likely to occur. When pi is 0.5, we have a nice even symmetrical distribution. And then finally, with pi equals 0.7, we have a distribution which is clustered around the high values, 7 and 8 mostly. And then we have this left tail, which means that this is a left skewed distribution or negatively skewed distribution. So the reason why I want to make sure we go over this is because we'll see that there's some similarities when we're dealing with continuous random variables. The difference, one of the big differences though, is that you have in effect an infinite number of bars with a continuous distribution. So instead of trying to illustrate it with bars, we're going to use a curve. Okay, we're going to have a curve which represents an infinite number of possibilities. So there's a few other key ways in which continuous distributions are different than discrete distributions. So we have an infinite number of values. Now, there is a formula here. There are formulas, but we're not going to actually solve them directly because they're simply too complicated. We're going to lean more heavily than usual on our calculators. And we're also going to potentially at least use a chart, a couple of charts which I have here, which I just posted, which we're going to look at so that we can use either one of them. Okay. So let's get into this. So here's a simple example of a continuous distribution. And you can see what's going on here. Suppose that we define X to represent the length of time until the next phone call arrives. Okay, now, if we were using the Poisson distribution, we might have asked a question like this. What is the probability that there will be, let's say, 5 phone calls in the next hour? And in a case like that, the number of possibilities is finite because that has to be an integer, a positive integer. It could be a 0, a 1, a 2, a 3, a 4, or a 5. This is different. The time that it takes for the next phone call to arrive has a fractional component to it. In other words, the length of the time to the next phone call could attain a lot of possible values. For example, it could be 3.7 minutes, which is clearly not an integer. It could be 4.718 minutes. It could be 5.01421 minutes. So you get the idea here. There's literally an infinite number of possibilities here. In fact, if you look at the real number line, starting at 0, all the rest of these values are possibilities. In other words, it's not just the integers, it's everything in between as well. So in other words, it's not just the case that this number has to be 0, 1, 2, 3, 4, or 5 or whatever. We can also have all these different fractional values as well. And you might recall that the number of possible values between two of these integers is infinite. So the number of possible times until the next phone call is infinite because of the fact that we have this fractional component to it. Okay, so in other words, we're no longer restricted to integers, which therefore means the number of possibilities is infinite. That being the case, we say that X is a continuous random variable. So remember, continuous is the opposite of discrete. Okay, now that does complicate things quite a bit. And that's why now all of a sudden we can no longer rely on a formula, although there is one. In order to solve for it, you would actually need to use calculus, which we will not be doing here. So in order to avoid using calculus, instead, we're going to either use our calculators or a table. Okay, now, the formula that we had in the previous chapter for calculating the binomial distribution, let's say, let's go back and revisit it real fast. This formula actually has a formal name in statistics. Okay, it's sometimes simply called a probability function, but if you want to be super technical about it, the formula that associates probabilities with a discrete distribution is more formally known, and let me introduce that here. For a discrete random variable, such as the binomial or Poisson, the formula that calculates probabilities is known as a probability mass function. Okay, now you don't have to remember that. I just wanted to point that out because when it comes to a continuous random variable, the formula that we'll be using has a slightly different name. Okay, slightly different. And you know that in statistics, there's a lot of terminology. We have to be careful about it because similar sounding names can mean very different things. So when it comes to a continuous random variable, we now have what's called a probability density function. Now, the key difference between the two is that with a probability mass function, there's only a finite number of different possible values of X. Okay, so a probability mass function has only a finite number of possible values and can be illustrated with a histogram. Now, those bar charts that we were looking at are more formally known as histograms. All right, so in other words, all right, let's find it. No, just a little further. This is it. This type of graph where we have frequencies, or actually probabilities on the vertical axis, and the possible values of our random variable are on the horizontal axis. The proper name for this type of graph is a histogram. I do not know the origin of that word. I believe it's Greek, but I don't know the exact meaning of it. In fact, since we're on the topic, why don't we find out? You might want to know. It could come in handy one day. It comes from the Greek root histos, wow, which means the mast of a ship and anything set upright, like the bars on a histogram. Well, there you go. That makes sense. It's like the mast of a ship. So in other words, the only thing that's missing is is the little cell. So in other words, we could actually put one in there ourselves. Oh yeah. Okay, so that's then all of a sudden it does look like the mast of a ship. So that's a histogram. Now, with a continuous distribution, we obviously can't do that because we need to have an infinite number of bars. So what in the world can we do about that? Well, this can be illustrated as a curve. So here's what you have to imagine. That imagine you took the binomial distribution, but you have, for God's sake, you have an infinite number of bars. So in fact, there's so many of them that they're actually not even bars any longer. They're actually straight lines. But let's just say that we have, instead of an infinite number of bars, we just have a lot of them. So as they get skinnier and skinnier, so we get more and more bars, you could visualize connecting them all with a curve. Okay, so that's essentially what's happening here. Instead of having a discrete number of bars, if we have an infinite, literally an infinite number of bars, their widths are actually equal to 0. Each one is essentially, what you're dealing with now is a series of lines. And as you recall from high school geometry, the width of a line is 0. So rather than trying to illustrate it with a bunch of bars, we're going to illustrate this with a curve. And so the curve itself is being used to calculate probabilities, because in the framework we're setting up, areas under a curve are going to correspond to probabilities. Okay, in other words, instead of looking at the heights of individual outcomes like we did here, for example, we know that the probability in this case of getting x equals 2 is 0.3, because that's the height of the bar. But we don't have that ability with an infinite number of bars. Instead, because each bar has a width of 0, what we're going to do is look at areas. So in other words, depending on what this distribution is, the probability of being between these two constants equals that shaded region. In other words, we don't know what this distribution is, but it is continuous. You can tell because it's a curve. So the probability that x is between a and b equals the area under this curve between a and b. All right, so now we're thinking in terms of areas. We have a curve instead of bars, and we have areas that represent probabilities. So when we calculate probabilities in this section, we're actually calculating areas. So we're actually using geometry in this case. And the formula, the probability density function, is designed to make sure that it obeys all the axioms of probability. In other words, what that implies is that the entire area under this curve equals 1. It has to, because being the entire area under the curve represents all the possible values of x. So the total probability has to be 1. Okay, so these are some of the key properties of what we're doing with these probability density functions. Now, if this all sounds very abstract, don't worry about it. Our ultimate job is to calculate probabilities, but it's important to understand what these graphs are telling us. Okay, so just in general, the probability that x falls within an interval, here I've got it as x and y, is the area under the curve between x and y. All right, so again, it's a very similar setup. Here's lowercase x, here's lowercase y, and this is the area of interest, and this is the probability of being between those two values. All right, now, here's one of the bizarre consequences of having a continuous random variable. Because if you look at this curve, remember, it is being constructed from a series of infinite numbers of bars, each of which has a width of 0. In other words, it is constructed from lines. All right, I can't really draw them. Ideally, they'd all be sitting right on top of each other, but let's just say, now a line has a height, but the width of a straight line is 0. So when we're dealing with continuous distributions, we're going to make the following statement. The probability that x equals a specific value is defined to be 0. Okay, so in other words, with the phone experiment, let me just add that in here. For example, if x is the time until the next phone call, the probability that x exactly equals 4.1712048 minutes is defined to be 0. Oh, now that's something interesting. And why is this happening? Because there's an infinite number of possibilities. So what? Well, if each of these had a positive probability, then the total of all of these individual probabilities would be infinity. And according to the axioms of probability, the total of these probabilities has to be 1. So the way we work around that little problem is to define each individual probability as having a probability of 0. Okay, so what that means then is that we will therefore only calculate probabilities for ranges of values. So in other words, for example, it may be that the probability that the next phone call occurs between, let's say, 4 and 5 minutes in the future is, let's say, 0.2. That you can do, okay? You can calculate the probability being between 2 points, but you will always assume that the probability of having a specific value is just 0. Okay, so in other words, it's not mathematically possible to have a positive probability for each individual value of x, because again, that would cause the total to be infinity when it needs to be 1. So each individual probability is defined to be 0. So therefore, we can only calculate probabilities for ranges of values, not specific numbers. And of course, that's not what we saw in chapter 6. You can certainly ask the question like, what's the probability of getting 3 heads on 10 flips of a coin? Of course, why not? But here, you can't do that because the number of possibilities is infinite. Okay. Now that's, again, another kind of strange idea. In this chapter, we're only going to look at intervals. All right, now, one of the consequences of this, which is kind of strange to think about, is that we no longer need to make a distinction between strictly less than and less than or equal to, or between greater than, strictly greater than, and greater than or equal to. And why is that? Well, here's why. Because when you think about it, what is this probability? Let me choose different letters. It's hard to show a difference between lower and uppercase x. Let's just put it like this. The probability that x is, let's say, less than a, less than or equal to a, equals the probability that x is strictly less than a, plus the probability that x is exactly equal to a. Okay, I think we'll all agree that this is true. Okay, so let's say a is 10, then This means that the probability that x is less than or equal to 10 equals the probability that it's strictly less than 10 plus the probability that it equals 10. Now, in the continuous case, because the probability that x equals a is defined as 0, that means that this probability that x is less than or equal to a equals the probability that x is strictly less than a plus 0, or the probability that x is less than or equal to a is the same as the probability that x is strictly less than a. That's one of the more bizarre consequences of this being a continuous random variable. We don't have to worry about this distinction between less than or equal to or strictly less than, because now they mean the same thing. And the same thing holds with greater than. Now, some books, when we're dealing with continuous probabilities, will use strictly less than or strictly greater than. Some books use less than or equal to. I like the less than or equal to better because this is what's really happening. This is true, but I think we should continue to use less than or equal to or greater than or equal to. But just be aware that they now mean the same thing. Okay, so that also implies the following. Okay, so again, if you're looking at the real number line, let's say this is 10. This probability is the same as because they have to add up to 1. Okay, so with all that being said, we're going to introduce the most important of all the continuous probability distributions, and that is the normal distribution. Well, I would have to say that if you're going to remember one thing from this course, this is the most important thing that you'll learn, because you'll see it in many, many different applications. We're going to continue seeing it throughout this course. It's not just something you show it once and that's the end of it. Like, for example, we're not going to do a whole lot with the Poisson distribution after chapter 6, but this is different. The normal distribution shows up in many different applications in practice. So it's used almost everywhere. It has a lot of convenient mathematical properties. It's easy to visualize what it means. And so you'll see this in like finance and economics and biology and psychology, and you name it. Any discipline that uses statistics leans very heavily on this normal distribution. Now, of course, this distribution itself has a very interesting history, and we won't go into that today, but during a normal 16-week semester, this is where we would have a golden opportunity to take out, get on the net and watch a couple of videos about the development of this normal distribution. It has, you wouldn't think so, but it has a very long and interesting history. Some of the characters that were involved with this, let's just say they were very interesting themselves. So what we're going to just do is understand what this thing is, and we're most importantly going to figure out how to calculate normal probabilities. We also, of course, need to understand its properties. So the first thing you may have, now this is something you may have seen, the graph of the normal distribution. Remember, we did say that we can no longer illustrate these continuous distributions with bars. Instead, we have a curve. So I'm going to draw a picture of what this distribution looks like, and you may realize that you've seen it before. It looks something like this. and is often referred to as a bell-shaped curve. And the mean is in the center. So it's a nice symmetrical distribution. But again, because there's an infinite number of possible values for x, it is a curve rather than a series of bars. Now, I think it's time for our first fun poll of the day. Oh man, the old ones are still here, aren't they? Oh God, now I forget how to do this. There we go. Oh, I forgot. The question goes here. This is the title. All right, pretty simple one. Yes or no? All right, let's find out. A lot of yeses. Okay. Yes, well, that's why, because you've probably seen it in other classes. Maybe you didn't have the full background, but you've seen it before and you've seen it used for different purposes. It lends itself nicely to a lot of real world applications, and that's why it's so popular. And in fact, originally it was developed to explain the relationship between heights of fathers and heights of sons. Essentially, the individual who was writing these research papers, Ronald Fisher, again, was explaining how there's a tendency for very tall people to be balanced out by very short people. In other words, the chances of being, let's say, 2 inches above average height are roughly the same as being 2 inches below the average height, and all the way out to the very tall and very short people. But so the idea here is that there's an equal likelihood of being above the mean and below the mean, but you notice most of the probability is centered around the center, and then it falls off very rapidly. So if these are heights, you could imagine that these are average height people, and then these are very tall people, and these are very short people. And so the chances of being either very tall or very short are pretty much the same on either side of this center. And there's a lot of areas where this is also true. In particular, we often use the normal distribution to model the rates of return to stocks in finance. There's a lot of empirical research that shows that the returns to stocks do follow, not exactly, but close to the normal distribution. So in that case, these could be very high rates of return up here, and these could be very low rates of return. And there's a tendency for them to balance each other off. Okay, so it's one of the most widely used in finance and other business disciplines, not just business though, other areas as well. All right, now this is the formula for calculating normal probabilities. We're not going to use it, but what we're going to do is notice a couple of important details here. First of all, we have our old friend pi here. Now, unlike in chapter 6, this pi is the same one that you learned in your early travels in math. 3.41141 ... Okay, so remember you learned about this and you use this all the time in high school geometry. You're talking about, the circumference of a circle, the radius of a circle, all these formulas were based on pi. You also saw them a lot when you were dealing with trig functions like sines and cosines, where pi was used to represent radians. All right, remember sine pi and all this good stuff. Yes, you do. You might cringe when you see, oh man, well, that's not what I wanted to do. You might cringe when you see this, but you remember it, don't you? Yes, you do. Now, if you look here, you'll notice a couple of our old friends have come back to visit. mu, that's of course the Greek letter mu, and this is our old friend sigma. Now, their meaning hasn't changed. You recall that we introduced these when we were studying populations, but they're also frequently used when we're dealing with probability distributions. So mu is the mean of the distribution. And sigma, as you can probably guess, is the standard deviation. Whoops. So the Greek letters are used for both populations and for probability distributions. Their meaning never changes. And of course, here's E again, which we saw with the Poisson distribution. So although it's hard to tell, if you were to draw this curve in a graphing program or in Excel, you would end up with this normal curve. Okay, so in other words, this formula generates this curve. Okay, now it turns out that there's a lot of information that we can obtain from this mean and standard deviation. Just like we saw in the previous chapter, remember we're seeing how with the binomial distribution, there's an infinite number of binomial distributions, each of which has a different value for n and for pi. Okay, so here, this is the case where we had 10 trials, or n equals 10, and the probability of success, or pi, is 0.2. And you can see this looks very different than the case where n is 10, but pi is 0.5 and 0.7. So with the Poisson distribution, the only thing that separates each graph is the value pi. So something similar is going to happen here with the mean and standard deviation. There's an infinite number of normal distributions, each of which has its own unique value of mu and sigma. Well, I'm going to show you some basic graphs which help you understand how these relate to each other. So for example, suppose we had two normal distributions that have the same standard deviation but different means. Oh, by the way, I forgot to mention one important detail back here. These curves literally go on forever. They do not stop. They cover the entire real number line. So they literally go on forever. In other words, they're defined for all real numbers. So that's an important detail in this graph that I'm about to show you. Actually, let me fix this a little. So there's two normal curves. And maybe I'll just do them in two different colors. Okay, so the important detail here is this curve has, let's say, a mean of 10 and a standard deviation of 2. Then the black one has a mean of, let's say, 1, but also a standard deviation of 2. Now, the key detail here is that the means are different between these two curves because they're located at different positions on the normal, the real number line. Okay, this is the real number line. We go all the way down to negative infinity and up to positive infinity. They both have the same standard deviation, which is why they have the same shape. Okay, the standard deviation determines the shape, which you'll see in a minute with another example. The mean represents the position or location along the real number line. Okay. So any two normal distributions with the same standard deviation but different means will have the exact same shape, except but they will be located at different positions along that real number line. Now, what about the case where they have the same mean but different standard deviations? Very interesting case. All right, well, let's take a look at it. So now, let's see. There's the first one, and now the second one, I'll make it red. Okay, now what's going on here? Well, they both have a mean of, let's say, 5. What's different, though, is that this one has a small standard deviation. Let's say it's 2. And this one has a larger standard deviation. Let's say that it's 5. So the key here is that they both have the same position because they have the same mean, but their shapes are different. They're still both bell-shaped curves, if you notice. But the one with the low standard deviation is less spread out. In other words, there's more area close to the center and less in the so-called tails. These are sometimes called the tails of the distribution. So the sigma equals 2 is more, in other words, you're more likely to be close to the center or mean with this red curve than with the black curve. The black curve is a little more spread out because it has a higher standard deviation. But they both have the same mean, which indicates that they have the same location. Okay, does that make sense? All right, so this is the meaning of, or this is how we can tell or recognize some of the properties of these curves by looking at their mean and standard deviation. Now, it turns out, though, that there's one specific case which is the most useful and the most widely used as a result. What could that be? Well, the special case we're about to look at is referred to as the so-called standard normal distribution. And all that means is that the mean is 0 and the standard deviation is 1. So this is the only normal distribution that has its own name, which shows you how important it is. The mean is 0 and the standard deviation is 1. This is the one you're most likely to use in practice. All right, so with that being said, how do we actually calculate normal probabilities? Oh, there it is again. There's the normal curve. I'd forgotten that I'd drawn a nice picture of it with Excel. One thing you can see from this curve, which you couldn't really see with my hand-drawn curves, is that the curve essentially, it doesn't stop. I mean, this is Excel. You know, Excel doesn't have the best graphics capabilities in the world. This curve actually does continue, but it's so close to 0 that you can really not even see it. Once you get up past 3 or down below -3, essentially almost all the area under this curve is between these 2 points. Now, what exactly do they mean? Now, you notice it says standard normal. which means that the mean is 0 and the standard deviation is 1. And by the way, here's just a little side note. Let me just mention this in passing here before we get back to this. By convention, we use x to represent a normal random variable, which is what we did with the binomial in the Poisson, except for the special case of the standard normal distribution. For this case, we use z to represent the standard or a standard normal random variable. Okay, it's just a convention, but you may have heard the term z-score, and the z-score refers to a specific point underneath the standard normal curve. Okay, so I just want to throw that in there before we carry on. And then I'd just like to point out that this curve is in fact the standard normal distribution, which means it's the letter z, which you can barely see it, but it's right here. Now, with this curve, we can easily interpret these numbers along the horizontal axis. For example, this is the mean. Right smack in the middle is the mean. This is mu. This 1, based on these values, could be interpreted as being 1 standard deviation above the mean. So in English, we call this 1 standard deviation above the mean. That means that this -1 must be mu minus sigma. Okay. Whoops, that's negative. That equals 1 standard deviation below the mean. Now, using this terminology makes it possible to directly compare results under one normal curve versus another. We want to think in terms of not these actual numbers, but how many standard deviations they are away from the mean. That's the important detail when we deal with these normal curves. Not so much the number, but how many standard deviations are we above or below that mean. And similarly, of course, this must be mu plus 2 sigma and mu plus 3 sigma. Down here. Oh, does no one want to ask a question? Oh, okay. Mu minus 2 sigma. And then, of course, this one must be mu minus 3 sigma. Most of the time, we'll be somewhere in that range. You can see it's extremely unusual to fall outside of the range. So in other words, all of these represent being within 3 standard deviations of the mean. This covers almost 100% of the entire curve. The area in these tails is extremely small. So in other words, this 4 is 4 standard deviations above the mean. It's very, very unlikely you'll run into that. If you were thinking in terms of heights, for example, this mu is the average height. Mu plus 4, this would be like somebody who's like 7'3", let's say. They're so tall that you almost never see anybody that tall. It's not impossible, but it's extraordinarily rare. Okay, most of the time will be somewhere in this range. Okay, so still, everything we've done is just been kind of building up to the calculation of the probabilities, which we're going to approach in 2 different ways. There are charts that were set up to do this directly for us. And those charts were, of course, meant for a period of time when we didn't have these high-powered, sophisticated calculators. With the calculators, the charts are really not necessary, but I still think it's important and useful to be able to understand what the charts are telling us. It's kind of like, you really need to learn the basics before you use the more advanced tools. All right, so with all that being said, I think we might be ready for our first actual example. So let me open up the charts so you can see what I'm talking about here. The ones that I just posted on Moodle, there are two of them. One of them covers the positive probability, or the positives part of the curve, and the negative. Now, the one thing you do want to notice with these charts is that they always are geared towards less than or equal to. Okay, so these are then formally known as cumulative probabilities. Okay, cumulative probabilities, meaning less than. Now, here, by the way, this chart, that's the other thing I need to mention. You see how it says here, the standard normal distribution? This is based on the assumption that for all of these probabilities, mu equals 0, sigma equals 1, and you can tell because of the little z here. Okay, so the example they're showing you in this little graph here is that suppose z is 1.34. What's the probability of being below that point? In other words, this whole shaded region represents that probability. Now, on the chart, the way they've structured it is that you can look it up by doing the following. Think of this 1.34 as 1.30 plus 0.04. The 1.30 is found in this first column. In fact, why don't we scroll down and find it? Why, there it is. Then we need, actually, let me make this a tiny bit smaller so you can see it all at one shot. The 0.04 comes from this column header right here. So when you combine those, if you go find the intersection between them, here we are. That area or probability is 0.9099. So all we have to do is take whatever value we have, break it up into two pieces. 1.3 comes from here. 0.04 comes from here. Okay. And at the intersection of those two, we have our answer. So it's pretty straightforward, except for one little thing. It only works for less than or equal to probabilities. Oh no, what about all those other cases that we might run into? All right, well, it turns out that we can take all the other cases and rearrange them algebraically to turn them into one of these probabilities. In other words, a cumulative probability. But that requires us to have a very thorough understanding of the properties of this normal curve. Okay, so that's what we have to do now. We have to dive a little more deeply into the properties of this normal curve. Now, the properties I'm about to show you apply to all normal distributions, but here we're specifically focused on the standard normal distribution. Okay, by the way, the negative table is set up to do the same thing, except with negative values. The areas below the mean, let's say z is negative 1.3. This one could be broken down into this plus, actually, the way we would write that is negative 1.3 plus 0.00. So the negative 1.3 comes from the first column. It's way, way down here. And then the 0.00 comes from the top row right there. So we're looking for the intersection of these two values, and we come up with 0.0968. And that is what this area is, 0.9068. Okay. Oh, sorry, I wrote it wrong. It's 0968. Hold on a second. There's a here it is. Somewhere along here, there's a way of erasing things. It's not set up very clearly, in my opinion. It's 0968. You can see it's a tiny little area. It can't be that high. 0.9068. 0.0968. There we go. All right, so that's what this chart is enabling us to do. But like I said, it's only good for this type of probability. What do we do about the other cases? Well, we're going to find that out. Okay. And then when we're done with all this, we'll do some examples, and then I'll show you some shortcuts. Okay. Then you can see the shortcuts. All right. Okay. So why don't we, oh, it's 11. Okay. So why don't we knock it off here for a typical, usual early morning break. We'll stop for about 10 or 15 minutes, just enough time to get some munchies, and then we'll dive into these actual calculations. All right. Is everyone agreeable to that? I bet you are. All right. So see you all in a few minutes. All right, so now we can get back into this. So in the slides, there's another example. For example, let's say if you were looking for the probability that z is less than or equal to 1. So here I've just got a small portion of the table. So the 1, remember, this is just the same thing as 1.0 plus 0.00. So after you break it up, then you can see that we can find it by looking at the 1.0 here, and the 0.00 comes from here, and then the result is 0.8413. So if this is our curve, this is the 1. Now remember, 1 means 1 standard deviation above the mean. All right, so this whole area, or probability, is 0.8413, or you could think of it as 84.13% of the total. Okay, now, imagine, like, for example, there's a test. And let's just say that the scores are normally distributed with the following mean and standard deviation. So let's just create a quick example here, how you can interpret this. So just imagine that there's an exam, like I said, which has scores are normally distributed with a mean of, let's say, 80 and a standard deviation of, let's say, 8. So this means that if your score is 88, this is 1 standard deviation above the mean. The probability of getting a score this high, or actually getting a score less than or equal to 88, is therefore 0.8413, or 84.13%, because this is the same as the probability that z, our standard random variable, is less than or equal to 1. Okay, so in other words, they mean the same thing. Having a z-score, as it's called, of 1 is the same as the score on this exam of 88. So let me just add that again at the end. Okay, so z-score comes from the fact that the letter z is used to represent the standard normal curve. So in other words, with a mean of 80 and a standard deviation of 8, if that's your score, 88, you are 1 standard deviation above the mean, which means you've outperformed 84.13% of the class. So that's how we can interpret this number. So it's fine to look this up in a chart, but it's nice to know what it actually represents. So in this particular case, it means that you've gotten an 88 and you've done better than 84.13% of the class. So imagine if your scores were written that way. Imagine yourself getting your exam back and it has a big 1 on it. And you think, oh my God, I got a 1. No, you got 1 standard deviation above the mean, which is 88. That would be interesting. All right, let's see. Do I have another example? Okay, yes. And so here's a picture of what we just did. Again, this is the standard normal distribution, so that 1 means 1 standard deviation above the mean. And that has a probability of 0.8413, or 84.13%. All right, now how about this one, negative 1.13? So again, think of this as negative 1.1. 3 is the same as negative 1.1 plus negative 0.03. Or I guess what you could do instead is just put a negative sign here. It doesn't really matter because the numbers across the top row are all positive. So you're going to look at the intersection of negative 1.1 and 0.03 to come up. This is the probability that z is less than or equal to negative 1.13, and that's 0.1292. So if you did this on an exam, that means you really bombed it. If your score is 1.13 standard deviations below the mean, that means you had a really tough time. All right, so now, what about, as I raised this question earlier, what about cases where the probability is not less than or equal to? Well, for those cases, we can use the tables, but we have to do some algebraic manipulation based on the properties of the standard normal distribution. What could they be? Well, first, we already knew this one. The entire area under this curve adds up to 1. And you'll recall the curve does go all the way out to positive and negative infinity. So this is the equivalent of, in the axioms of probability, remember we were told that the sample space has a probability of 1. That's essentially what you're seeing here. One of these probabilities one of these outcomes has to occur with certainty. So the entire curve has to have an area of 1. So when you get a result like 0.8413, for example, like we did before, that means 84.13% of the total. All right, now that's an important one to know. Now, number 2, remember with the standard normal distribution, the mean is 0. So the curve, if you recall, is symmetrical. And that means that the area below the mean and the area above the mean are identical. The left-hand side and the right-hand side are mirror images of each other. So the only way that can be true if the total area is 1 is if the area on either side is a half. So in other words, what you're seeing here is that the probability of being below the mean is a half, and the probability of being above the mean is also a half. It has to be, because that's the only way that these two probabilities can equal each other and yet still add up to 1. Okay, so this is below the mean, and this is above the mean. Okay, so that's an important detail. And this is because the symmetry of the distribution. The left-hand side, everything below the mean is a mirror image of everything that's above the mean. What else is there to know? Well, some of the consequences of these are, if I want to calculate a greater than probability, in fact, let me do this with a diagram. Now, just a few minutes ago, we saw that the probability of being less than 1 is 0.8413. Because the entire area must add up to 1, that implies that this area is equal to 1 minus 0.8413, or 0.1587. And you notice that both of these are less than or equal to. We don't have to worry about whether it's strict equality or strict inequality. So by knowing that this whole area is 0.8413, which we looked up earlier, that tells me that this probability is going to be 0.1587 because these two do in fact add up to 1. So already we know how to deal with greater than or equal to probabilities. Nice. All right. So in other words, the chart is becoming more and more useful, isn't it? All right. What about a case like this? Oh, and yes, this is the one we just did. You can see that these have to add up to 1. So algebraically, that implies this. So in a case like this, you would look this one up in the table, and then you would subtract that from 1 to come up with the actual probability that you need. All right. Now, how about another example? Let's look at negative 1.59. Now, we're being asked to find the probability of being above negative 1.59. So what we can do is look up this area in the table. Okay, so let's go to the negative chart. Negative 1.59 is found. All right, let me erase all this other stuff. Okay. Negative 1.59 so the negative 1.59 equals negative 1.5 plus, or actually minus 0.09. So the negative 1.5 is right about here. And the 0.09 is way over here. So at their intersection, we have 0.0559. Oh, there we go. We can see it all. So that's the area in the below negative 1.59. What about the shaded area, which is what we're really interested in? Well, then what we're going to do is take 1 minus the probability of being less than or equal to negative 1.59. And so what's left is 0.9441. And that's our final answer, 9.9441. So we're still using the chart, but we still have to go through this extra step because of the fact that it's not a less than or equal to probability. So what other cases might we encounter? We have less than or equal to. We have more than equal to. Oh, well, how about this one? What about in between? Ooh, are we allowed to do that? Yes, of course we are. So how would that work? So this one is the area between 0.72 and 1.83. Oh boy. What can we do with this one? We're going to use a clever strategy. Watch this. All right, so again, it's the area between 0.72 and 1.83. Now, watch this. The area to the left of 0.72, which we can look up on our table, is this. And then the area below 1.83, let's use a different color, would be this. And so while we're at it, we may as well go look those up in the table. So 0.72 comes from the positive table. .7 can be written as 0.7 plus 0.02. That would be the combination of 0.7 and 0.02, 7642. So this red area has an area of 0.7642. The green area, 1.83, can be calculated as 1.83 is 1.8 plus 0.03. The 1.8 is way down here somewhere. Way down here. And then we have 0.03. The intersection between the two is 9664. So that green area is 9664. The area that we really want is right here. So what we're actually going to do is this. We're going to take the larger green area and subtract the smaller red area. And what's left over is what we're looking for. In other words, the green only section. So we subtract and we're going to get 2024. Okay, so it's the difference between the two cumulative probabilities. Oh, whoops, it's sorry, my fault. It's 2022 right here. This is a 2. So it's just the difference between the two. Okay, so once again, you can write it out more formally. This equals the probability that we're below 1.83. This is the probability that we're below 72. Oh, I forgot. What did I do that for? This is not X. This is Z, of course. And that's what we have to do. So that pretty much covers all the cases. We have less than or equal to probabilities are on the chart. Greater than or equal to, we can find by manipulating the equation, we can subtract 1. Let's say something like this. And here, when we have in-between probabilities, we just subtract the larger from the smaller, or the smaller from the larger. And that's all we need. All right. Now, here's a slightly more challenging one because these are both negatives. But it shouldn't be a problem because it's the exact same logic. We're looking at the area between negative 2.05 and negative 0.67. So we're going to have the difference between these two probabilities. This is the larger probability, by the way, and this is the smaller one. So I've already gone ahead and looked these up for you. And the difference between those two is 2312. And that's all you have to do. All right. So far, this isn't too bad. Oh, one more possibility here. All right. What if we have an in-between probability where one is positive and one is negative? Well, again, it's not a problem because conceptually it's exactly the same procedure. By which I mean we're looking for the area between negative 1.04 and positive 1.33. So once again, we're going to take the larger of the two probabilities and subtract the smaller one. So I went ahead and looked these up in the tables. And this is what we get. 0.9082 minus 0.1492 is 0.7590. And that's our final answer. Okay. Not bad. All right, now, up to this point, all of these examples were based on the assumption that we were looking at the standard normal distribution. Now, not all situations are based on the standard normal distribution. You could easily have cases where a variable is normal, random variable is normal, but is not standard normal. So is that a problem? Not exactly, but it does require one extra step in order to use our charts. What could that step be? Well, we have to make a conversion to convert our current or original values into the standard normal case. And the formula for doing this is very simple. It is, this is it right here. This is a key. This is a very big deal right here. So we're assuming here that X is normal, but not standard normal. It has some mean other than 0 and a standard deviation other than 1. But here's the issue, and here's what makes this so interesting. If I take X and subtract its own mean and divide by its standard deviation, the result is a standard normal random variable, which we sometimes think of as a z-score. So if I have a case like this, where X is not standard normal, I can still use my charts, but first I have to make this conversion. Then I'm all set. All right. Now, of course, in reality, you're often going to run into these cases where X is what we're dealing with rather than Z. So it's important to know how to do this. All right, I believe there's an example coming up. How about this one? As I mentioned before, sometimes we assume that the returns to stocks are normally distributed. So here's a case where we have the return to a stock, which is assumed to be normal. The mean is 5%, the mean return, and the standard deviation is 2%. So X is normal. It's a random variable that represents the returns of the stock. X is normal, but it's not standard normal because the mean is 5%, which, by the way, I'm going to rewrite that as 0.05. I find it easier to deal with the decimals. And the standard deviation is 0.02. Now, we can calculate probabilities for the stock using our tables as long as we make sure we do the conversion properly. All right, so how would that work? Oh, well, we're going to ask the following three questions. What's the probability that the return of the stock over the coming year will be A, 4% or less, B, 8% or more, and C, between 4 and 7%? Okay, so let's start with A. So we're looking for this probability. So what we're actually doing, before we do that, let me show you a graph. What exactly are we accomplishing right now? With that formula, I mean. So remember, this is X, the mean is 0.05, and the standard deviation is 0.02. Down here, we'll have Z. Actually, I can cheat a little bit here. Watch this. I think I can just copy it exactly. Ooh. Just to make sure that they have the same shape. That's what I'm really interested in. Okay. So a mean of 5 in this distribution corresponds to 0 down here. A value of 7% in this distribution. This, if you notice, this is one standard deviation above the mean. So that corresponds to a value of 1 down here. 0.09 is 2 standard deviations above the mean, which corresponds to a 2 under the standard normal curve. 0.03 is 1 standard deviation below the mean, which corresponds to -1 down here. And then 0.01 corresponds to 2 standard deviations below the mean. So therefore, let's say I wanted to know the probability that X is less than 0.07. That means that it's the same as the probability that Z is less than or equal to 1. And that I can look up in my chart. Okay, so in other words, this 0.07 is 1 standard deviation above the mean, as is 1 down here. So if I need this probability, I can easily look it up in the chart by looking for 1, because they mean the same thing. In a way, what we're doing here is we're really just changing the scales. It's almost like converting from Celsius to Fahrenheit. It's really the same thing, because obviously, if I told you that the temperature is 32 degrees Fahrenheit, it means the same thing as telling you that it's 0 degrees Celsius. So here it's the same idea. You're just changing the scales, but in such a way that it's now possible to use our table to come up with any probabilities that we may need. All right, so now that you know what we're actually doing, and of course, this is all coming from this formula. That's what this is doing. It's converting what's going on in the X distribution into the standard normal down here at the bottom. All right, so in our example, we're looking for 0.04. Now, if you plug those numbers into this equation, .04 minus 0.05 over 0.02 is the same thing as saying, what's the probability that Z is less than -0.5? So if you're to go back to this curve, let me just do that real fast. 0.04 on the top curve is the same as -0.5 down here. And we just proved it with that formula. Okay, so 0.04 is mu minus 1/2 sigma. All right, and we can go look at our chart. And let's go get to the negative chart. Negative 0.5 would be a very simple one. It would be the intersection of negative 0.5 and 0.00. All right, let me just do this again. Oh, that's very sloppy. Okay, so the intersection of those two, we get 0.3085. So let's go back here, and you can see that this probability, these are the same, 0.3085. Okay, this is Z, this is X, and these are the same. And we can see that because of the formula. Z equals X minus mu over sigma. All right, and of course the chart is here, the graph is right here, and that of course means the same thing as being below negative 0.5 on the standard normal scale, or that probability is 30.85%. Now, how about this one? Ooh, greater than 8.8. Now, here, when we convert this, so remember, the mean is 0.05 and the standard deviation is 0.02. So this is the same as Z being greater than 1.5 or 1.5 standard deviations above the mean. That we cannot look up in our table directly. So we resort to this wonderful property where what we have to do is instead look up all of this and subtract it from 1. All right, so I've looked this up for you in the table. It's 0.9332. So this little piece up here is only 6.68%. So The bottom line then is that the probability that our return is above 8% is only about 6.68%. So this one had two complications. First, we had to convert into a standard normal form, and then we have to use this approach to come up with a number taken from our tables. So the bottom line is that this probability is 0.0668, not very much, not very high. All right, so there's one more case here where we're looking at an in-between probability, which means we have to apply this conversion twice and then look up two probabilities in the table. So it's a little bit trickier. Okay. So that's our final result. Now, how about this one? Oh man, look at all that work we have to do. So this means that this probability using the standard normal distribution is the equivalent of being between -0.5 and +1. And we saw earlier that we cannot do that directly. What we have to do is calculate two probabilities, each of which can be looked up in the table. Okay, so you can go directly to the tables. I've already taken care of that for you. The difference, the difference between these two is what we're looking for. All right, there it is again. I've looked up the values for you, and of course you can see the difference is therefore your answer, which is 53.28. Okay, and this is the probability that our actual returns are between 4 and 7%, which is what we're really after. All right, and then of course the graph is right here. It's between -0.5 and +1, and it works out to about 0.5328. Whoa, that was a lot of calculations, wasn't it? A lot of new concepts flying around, but it is Monday. I guess we're okay. On Monday, we can certainly handle a lot of new ideas. So what we're going to do next, not today, but next, is we're going to see some shortcuts for calculating these probabilities. And then we're going to take a very interesting case where we can, it turns out, we can use the normal distribution to come up with approximate probabilities for the binomial distribution. So we'll do that tomorrow. And when we're done with all of this, then we can dive into chapter 8 already, which is a bit of an extension of what we're doing here. We're going to go back and revisit the concept of samples and sample means, and we're going to apply the normal distribution to them in a very specific way. In the meantime, I think we've all had enough for one day. So we're going to finish right here. Nothing is due right now, not just this minute. But if you have old work out there that you haven't finished, then I think you should get it in as soon as possible. So now a few eager beavers have already sent in their midterms, and that's fine. The sooner you send that to me, the easier and quicker it'll be to correct them. But for the rest of you, don't worry, it's not due until next Monday. And so, but probably we'll also have some new problem sets due later this week. So, all right, I think for now we're done. And so tomorrow we'll wrap up chapter 7 and we'll do as much of chapter 8 as we can. Nice. Okay, good. So I guess I'll just see you all tomorrow at the same time in the same place.
Have a good one.
All right, see you tomorrow.
Professor, I have a question actually.
Okay.
Did you receive my email last night by any chance?
Oh God, I can't see your name here.
Oh, it's Arbaz.
Okay, what was the question?
Um, so I emailed problem set 3 and 5.
Oh, was it last night? I wasn't here last night. If you sent it to me after, let's say, 6 or
Yeah,
7.
I mean, I did them. No, I did them like when they were due, but for some reason, I sent them to your Gmail, and then like for some reason, you never received them.
Oh, you know what? They probably went to my junk box.
Oh, okay.
I'll look. But did you resend them last night?
Yeah, I resent them last night on Outlook. So just
Okay, that's fine. All right, I'll
yeah.
take care of it then. Good.
Okay. Yeah, I'm not gonna have like any late points, right?
No.
Okay.
That's fine.
Okay. And thank you so much.
Okay, you're welcome.
All right. Thank you.
All right, bye.